Okay, it's time to start a new RIANA webinar. Hope that everyone is hearing us and see us. So hello everybody, I'm Nicu Scărișoreanu and welcome to this new RIANA webinar. It is my pleasure to introduce Cătălin Constantinescu to you, to RIANA audience. And Cătălin Constantinescu is a well-known researcher at LP3, Marseille. So he will discuss and he will present us this talk entitled Additive-Subtractive Synergy in Ultrafast Digital Manufacturing, talking about tunable femtosecond to picosecond laser processing for highly selective ablation and printing in thin films, electronic and photovoltaic applications. So, Cătălin, please start your presentation. You have 30-35 minutes. Thank you.
Thank you. So yeah, it's a very long title. Hello, everyone. Thank you, Nico, for introducing me. I will be discussing today on how ultrafast lasers enable a true additive-subtractive digital manufacturing synergy by using femtoseconds to picoseconds pulsed lasers. The focus will be on selective printing and ablation for thin film electronics and photovoltaics, illustrated with a few examples developed at LP3. And before going into the physics and processes, let me briefly set the geographical and scientific context and also the social, if I may. So Marseille is situated in the southern part of France at the Mediterranean Sea. The lab is situated here. And just to enjoy the, let's say, the campus and the Lumini here, this is a live, actually it's a photo I took a few minutes back. And here in Lumini campus, the lab is at the interface between laser physics, material science applications. It's a very small lab with around 30 people, including the permanent personnel from the CNRS and the Aix-Marseille University. Students including master students and PhDs, but also postdocs and visiting staff. So this campus, it's a natural environment that supports cross-disciplinarity. We have here labs from different, let's say, backgrounds. We have oceanography, mathematics, chemistry, but also all the way to nuclear and particle physics. So continuing about this ecosystem and what we do here at LP3, we need to understand what the ecosystem is driven by and the concrete technological and market needs. So for that, I will discuss about the requirements and the market context. In the particular, the printed and flexible electronics, which impose strict constraints regarding cost, speed, resolution, compatibility, and in particular with the flexible substrates, which require low temperature processing. The market growth clearly shows why digital maskless technologies are essential, especially for sensors. But also for radio frequency ID tags and also, and very important, concerning energy devices. However, our approach at LP3, which is a laboratory that deals with lasers, plasmas, and the photonic effects, is to understand why lasers are so powerful in this context. And we need to recall a few basic light matter interactions. So for that matter, I would like to just draw attention about the laser matter interaction, which relies on the dual, let's say, dual nature of light, the understanding of how a photon energy governs the electronic excitation, while waves properties define propagation, fluence and intensity, which are key parameters that directly control energy deposition in materials. And all these principles are at the heart of what makes a laser, right? So what's a laser? Starting from Maxwell's equations to Einstein's stimulated emission, the theory behind it, and how lasers combine coherence, directionality, and high energy density. This is precisely what enables extreme spatial and temporal control of matter. So lasers and light is important in science as much as is important in art. So this image of Claude Monet, who once said that light is the most important person in the picture. This is one of my favorite things that we can combine science and art. So moving forward, the idea of lasers, once they existed, the question rapidly shifted from can we build one to what can we do with them? So today, in just when we look back, in just a few decades, laser the devices moved from laboratory curiosities by a giant. They had a giant leap. So they became from ubiquitous tools to gadgets to devices which are used currently in surgery or in telecom or in manufacturing and research. So lasers, they can be ultra fast, and actually the ultra-fast lasers are the latest step, opening non-thermal processing regimes, which is actually the point of our webinar today. So this versatility also comes from the diversity of laser sources which are available today, and that's really, really important because if we consider lasers from infrared to ultraviolet, the wavelength selection, which allows us to tailor absorption mechanisms from phononic to electronic to nonlinear, depending on the material and the targeted processes. And for example, in our case here at LP3, most of the experiments that we do with this ytterbium YAG, yttrium aluminum garnet, that works at 1030 nanometers. Which can be also, we can use the superior harmonics and also the neodymium YAG as well. So this brings us to, let's say, to the aspect of how light actually propagates and how it that at very high intensities, ultrafast lasers trigger nonlinear absorption, enabling photoionization, photodissociation, even electron emission in transparent materials. So this is a key for precision processing. So all these effects must be considered together in the global laser matter energy balance. And for that, when the processing outcomes depend on a delicate balance between the laser parameters, the beam profile, the surface morphology, the material, the intrinsic material properties, these are really, really important. And for that matter, pulse duration is especially critical. So the laser I mentioned before, the ytterbium YAG, it's actually a tunable laser. So we can tune from picosecond to femtosecond and back. So let's now move from fundamentals to additive laser processing. Why lift? Simply, this technique, LIFT, which stands for laser-induced forward transfer, is now a fully digital, which means that we can fully control it with a computer. We can use designs that can be rendered by a software. and is a single-step printing technique compatible with virtually any material and substrate. The whole idea is to use a donor substrate which is transparent. The laser beam is focused at the interface between the donor substrate and the thin film. The thin film can be solid, like a simple thin film or a multi-layer structure, or it can be a suspension, like a gel or a paste or ink. So without further ado, the whole idea of presenting this technique to you is that it bridges micro and nanoscale manufacturing with excellent position accuracy. So to understand its potential, let's further look at the basic lift principle to understand it properly. And for that matter, the whole system is simple. So we have a laser source, which can be working at any wavelength needed. And this is important because we need to understand how the interaction with the matter, with the donor, takes place. The beam is shaped through a lens or through a system, and it can be also positioned with another type of system. And as I said, so for example, in this case, we use a mask that, and the image of this mask is set at the interface of the donor, such that we can detach and transfer on a receiver substrate, which is in a close proximity of the donor. Usually, it can be of a few tens of microns, all the way to a few hundred microns, depending on the needs. And we can also use simple thin films or complex thin films. We can use direct irradiation, or we can use a dynamic release layer, which decomposes and propels the what we call the flyer or pixel. We can do it in air, or we can do it at low pressure, in order to take advantage of the fact that there is no shock wave, because remember, this is an explosion. The transfer is like an explosion. Furthermore, in order to understand on how can lift enables sequential printing, like for example functional stacks, like electrodes and dielectrics. Like in this case here, we see that we printed capacitors. We didn't use masks or chemical steps. We printed on flexible substrate. So this naturally leads to fully functional electronic devices. In this case, a fully functional microcapacitor, which was made from an electrode of silver, a thin film of silver of 300 nanometers, with a parallel C of 400 nanometers. And by adjusting the thickness of the dielectric or the size of the pixel, we can control the capacity. This was a collaboration a few years back with another lab here in Lumini, SINAM, which is an interdisciplinary center of nanoscience. We had several collaborations with them, actually. So in this case here, we show results on how we transferred transistors. So these results demonstrate operational organic transistors fabricated by lift on a multi-layer. So we can see here that we have the metal electrode, the dielectric, and the organic semiconductor. And we have two types of architectures, as you can see here. And such results rely strongly on positioning accuracy, as you can see here. And for that matter, we can also let's say understand how this precision is at the heart of lift by understanding how we by explaining how we printed fully organic this time devices. In this case, we had an electrode of P.PSS and a pixel of semiconducting material, which is PQT12, a polyquaternium thiophene. And in this case, let's say the fact that we printed in several steps, so it's a technique that allows multi-step device fabrication with excellent reproducibility because we printed several devices. This can be integrated, and therefore it's essential for organic electronics and microelectronics in particular. So this precision also enables printing of advanced nanomaterials, like, for example, a few years back in a collaboration with another lab, this time in Romania, we had printed carbon nanowalls. This structure is a graph carbon allotrope. So if we consider fullerenes as 0-dimensional, nanotubes as 1-dimensional, therefore graphene is 2-dimensional. Well, this graphene stacks, which are grown perpendicular to substrate, transparent or not, are called carbon nanowalls. So they are empty, they're porous. So these carbon nanowalls combine porosity, conductivity, and flexibility. And with the help of lift, we preserve these properties, and we can therefore render them ideal for flexible electrodes. And in this case, we printed lines. So you can see here the pixels. We can print them close to each other, like an adjacent printing. And therefore, we prove the concept. Furthermore, beyond solids, lift is also highly important and extremely powerful for liquids and soft matter. So in this case, going from solid materials like here and here, we go to liquids, gels, and even inks like suspensions. And for that matter, we need to understand how the rheology, how the donor preparation, and the dynamics of the printing process take place. So in order to understand how things go, we need to optimize the droplet size, because in this case, we don't have a pixel anymore. We have a droplet. We have a jet which forms, and we have a way of collecting this on a donor, on a receiver from the donor. And in order to understand how the process takes place and how we can optimize the droplet size down to a few tens of microns, like, for example, we can get droplets, I think the smallest we had is 5 microns. We can print whatever we want, and I'll show you this. But first, let's visualize how this jet forms, because this is at the very heart of printing droplets. So, understanding liquid jet dynamics. In here we have a sequence which illustrates how a bubble form, how the jet follows, and how the droplet is landing. So these are the key stages in governing resolution and stability. And the simple setup of lift really helps a lot to control this properly. So here you have the schematic, and here you have the actual image of the donor, this glass slide, which is covered in silver nanoparticle based ink, which was made by spin coating because it was highly fluid, and the donor, which is also a glass slide in this case, but we can change it with the different material. So coming back to the jets, a process window needs to be carefully defined. So for that matter, if the energy is too high, the jet will destroy the bubble. The energy of the laser will destroy the bubble. If it's too low, the jet will not form properly. And if we are in the process let's say the proper parameters, the process window, then we can get a jet and therefore a droplet. And with this in mind, we can use the droplets either to print one next to the other or over one over the other one, and therefore create from droplets to continuous lines. In this case, we printed some structure, the meanders that can be used for various applications. So we need to understand how this process takes place, how to understand how tuning the fluence, how tuning the gap between the donor and the receiver, and the overlap of the droplets need to be taken into consideration with respect to the rheology of the material used. So therefore, we identified the regimes that produce continuous lines without the splashing, which is crucial for the functional printing. So this enables real device fabrication. So by controlling the droplet overlap and understanding how lines are formed, we can print continuous lines, structures, so on and so forth. And even we can, with the help of the software that we use, transform real images into printable structures. So in this case, we combined an image which was transformed into a printable thing with some text, just to show how this goes. And again, the resolution is sufficiently good for microelectronics. And this in this slide, these examples show how conductive tracks and patterns can be rendered compatible with flexible substrates. Furthermore, as graphene is a particularly illustrative case, here we present. This was a test we did a year ago with some colleagues from Bucharest as well, and this was a collaboration on how to print graphene inks. So we printed from commercially available inks. We did a drop cast donor sample. We printed first some droplets to understand how the lift process takes place. Then we controlled the overlap of the droplets, and then we printed various structures. These were used as resistors, as heaters for heating applications. So beyond the graphene, also other systems can be imagined. So for example, we also tried colloidal systems, which are easily accessible. This is a collaboration, again, with some colleagues from Bucharest, from Romania. In this case, this is a homemade latex suspension of beads, which can be, which are self-assembly, which can self-assemble in photonic crystals. And this is really important because with this sort of materials, we can understand how colloids enable hierarchical structuring and nanoparticle assembly. And this opens the routes toward photonics and sensing. In this case, we tried just to understand how we can control the printing by various techniques. So for example, adjusting the laser parameters, the lift positioning of the donor to the receiver. Also, we did some plasma electrowetting of the substrates, donor and receiver. And finally, this was an idea to create structures that can be used in anti-counterfeiting applications. So to further expand material compatibility to other types of materials, and the whole idea is to create a lift printer, which can be eventually a universal printer if you want. So in this case, we used double pulsed lift developed in LP3 by our colleagues Patricia Aloncle and Philippe Delaporte. This was a thesis a few years back, and the whole process is really simple. Instead of using one pulse to print, we use two. So we start from a solid thin film donor, and we use a first pulse of a laser, microsecond, for example, that will interact with the donor. It will melt locally the donor. It will create a pool of molten material, and then a second pulse will just eject this melted material and create a droplet. The whole idea of double pulse lift is that it decouples melting and propulsion, and therefore allowing virtually any material to be printed. So again, this is a step forward to a universal printer. My whole idea, for example, for this is to use it with the high melting temperature materials like titanium carbide or tungsten or other similar materials. And let's now, so if we compare this droplet size, then we can see here that we can print even below micron, so a few hundred nanometers. And furthermore, we can print by stacking them, so we can create pillars. As a joke, originally coming from Romania, impaling Vlad the Impaler, Dracula, etc. So this was funny as an application. So now let's continue to understand how the complementary technique goes. So we discussed about printing until now. So now we'll discuss about de-etching. So this is the subtractive processing approach. It's the same setup. So we can print as you, if you compare to photographs, we can print in positive or in negative, additive or subtractive. So in this case, subtractive means that we can ablate selectively with high accuracy, again by using the same setup. We just take out this part, and as the beam can be used to scan the surface, and for that I will actually show you the video. It will speak more than and properly than I do. So here it goes. Actually, I think I can leave the sound. So the scanner provides direction. It's the laser beam at the surface, and by scanning the surface, the material. So in this case, it's Kapton, which is polyimide, a flexible polymer highly used in electronics. The laser is it's an ytterbium YAG tunable laser, picosecond, femtosecond, so we can control the thermal effects on this substrate. This is what we did. This is just a test. And by controlling the overlap and the size of the scanned area, we can control the rastered area. And I will show you another. In here, we actually etched the meanders. This is something we tried yesterday just for a test, for a calibration test. With my colleague, Patricia Aloncle. So you see here the setup, the controller, it was a controller and then the scanning, and you see how fast it goes. The laser has 60 kilohertz repetition rate. So it takes very little time to actually scan. So the best part of this setup, the synergy behind it, is that we can use it to print such structures, but also to etch. Printing and etching basically takes the same time. So it's a very fast, process. So now I'm just showing how etching of a multi-layer structure can take place by controlling the fluence. By controlling the fluence, we can control the size of the ablated material, the deep, the actual deep that we can achieve, and again by adjusting the overlap, by controlling the surface quality, we can control the uniformity of the structure. So this leads to highly ordered patterns, which is really important. We have various types of etching at picosecond at lower or higher energy, so on and so forth. We can even change the wavelength. As I said, we can use superior harmonics by using specific doubling crystals. And we can also understand what happens when we change the pulse duration. So if here we had 10 picoseconds, for example, here we use the laser at 213 femtoseconds in order to understand how this goes. So these micro patterns illustrate the precision achievable with ultrafast laser processing for subtractive applications. So if we compare again femtosecond to picosecond, we see that the effects are different. Because of the way the laser interacts with matter. This is really important. I will not go too much into details. These are just some applications we have currently developed here in LP3. I'll just show you some details about how the pulse duration can affect the how to call it, the results. So briefly, when we use, for example, here picosecond, or we can use here femtosecond. Sorry. So here is femtosecond. Here is also femtosecond, but we scan the let's see, the overlap here is combined with an overlap of a next scanning line. So here we scanned 3 lines just to see how it goes. So we scanned in femtosecond in order to ablate a structure which is in this case a multi-layer of 3 different thin films. And by changing the pulse duration, look, so here we have picosecond, which is for the moment something we need to further process to understand how this is taking place, how this examples of ablation of subtractive case studies can be controlled in order to achieve nano and microstructuring across various materials, and therefore demonstrating their scalability and repeatability. So one other thing that we can do with these materials is related to creation of other types of structures. I will just explain a bit on how ablation under a specific background takes place. So for example, here we generate in this setup nanoparticles. Again, I will leave the video play. It's better to show than to explain first. So as you can see, we scan the material. In this case, this is a magnetic. This is a magnetic material. It's called permalloy. It's an alloy of cobalt and nickel. It's highly used in magnetic applications for controlling the field lines. And by creating these nanoparticles in a liquid, by controlling the parameters of the laser, we can control the size of the nanoparticles very accurately. So they are highly monodisperse. Another application, briefly, is related to lasers and microbeads, transparent microspheres, which act as lenses. The whole idea of this structuring of microspheres is that they have a natural way of ordering themselves. So this is a hexagonal compact structure, which is how to put it, highly useful in creating photonic nanojets. So these nanojets are concentrated light. They actually can concentrate light below the diffraction limit, enabling therefore nanoscale ablation with conventional wavelengths. So this concept can be extended further. It's easy to produce these monolayers of spheres. We produce them on at the interface between water and air in a modified Langmuir-Blodgett setup, and then we can collect these spheres on a choice substrate. And since they are highly oriented in 2D single layer, we can use them as 2D materials, so they actually diffract. So we can see here a diffraction pattern. This was just for the fun of it. And in order to understand how this takes place, by combining the laser parameters and microsphere size, we can achieve multi-scale patterning in a single process. This is a parallel process, so it's not a serial. We can print one after the other. We can print all at once. So this requires accurate understanding of how it goes. So the setup itself relies on the mis-scattering and the control self-assembly, which is, let's say, very important in order to understand how the size of the spheres influence the size of the nanojet, the photonic nanojet that appear. Just to show you an example, we used here a monolayer of spheres, which are 5 micrometers in diameter, and the nanojet that ablated in a tantalum thin film deposited on a silicon substrate created this structuring matrix. So the whole idea of this structuring, this printing, this subtractive applications, this is just to illustrate how the maturity of our approach here at LP3 it's currently taking place, and to further show that all these techniques are available in the RIANA consortium framework. So with this in mind, I will just again show a bit about how this can be part of the RIANA consortium. So with this in mind, I will thank you for your attention, and of course, if you have questions, I'm open to them. Thank you.
Thank you, Katalin, for this very interesting presentation. And of course, questions are more than welcome to see if everything was clear. So yeah, please, if you have question, I have one actually. Katalin, how do you see the application of lift technique for printing inorganic materials? And here I have in mind amorphous material, but also crystalline material. There is any future exciting, of course, the Vlad the Impaler type of applications?
So printing in solid state in organics, we can print either keeping them solid or transforming them, getting a phase transformation like melting. So if we melt them, will they remain the same in stoichiometry or not? This is also very important. If we keep the stoichiometry, then we can just melt them and print them in a double pulse approach. If we cannot melt them because they can suffer chemical damage, then we print directly in solid state. And by controlling the laser parameters and the mechanical setup of lift, then we can print solid state pixels, not droplets.
Have you targeted the possibility to use a sacrificial layer also in this case, for example, for amorphous materials?
It could be done. It depends on the material. So every application needs to be tailored.
Okay.
Every lift printing needs to be adjusted. We need to control the parameters. We need to understand the photochemical effects, if there are any. We need to understand the mechanical transfer, how it takes place. If it's in solid, then we need to understand if the material is brittle or not, how the elasticity of the structure. You need to understand how it will behave under high shock, because the laser pulse is actually a very high shock. On the other hand, when we deal with liquids, we need to understand how the rheology of the material takes place. If we combine the two in the double pulse approach, then we need to understand how it melts, how the rheology influences the printing, the transfer, and at the end, how it will solidify.
Okay, I think there is another question from Gitasu, I think. I don't know if my pronunciation is correct or not.
Yeah, thank you very much. I think my name is Getasu. So,
Okay.
My question is, I think, can you use this lift method for example, printing a perovskite, active perovskite on the, for example, ITO glass? You know, perovskite is a very highly disordered material. And so is it possible also to use this lift method, for example, with a very low energy and keep its uniformity? And what about it? Can it possibly also improve the performance and stability in this solar cell? Because it is a bottleneck in this area of solar cell is performance and stability. Thank you very much. Thank you for the very nice talk.
Thank you. Thank you for the question. This is a very interesting question because perovskites are a particular type of materials. If we damage the structure, we completely change their electrical properties. So for that matter, we need to understand the application. If we need to print a pixel of perovskite on a receiver material with the accuracy of lift procedure, we need to understand first how thick the perovskite thin film, the donor thin film, needs to be. We need to understand how it can withstand the forces during printing. Okay, I've never tried perovskites to print them by lift. Furthermore, we need to understand if we can add a protection layer, if we can use a dynamic release layer. All these parameters need to be tested. So if in the beginning it's a rather empirical technique, at the end, by understanding the mechanism, we can model them and we can draw a proper conclusion of it, and therefore use it from a lab approach to a industrial transfer, towards industrial transfer.
Okay, this is another question. How can you upscale the lift technique, or there are some progress there?
As far as I know, there are some companies that use lift for this synergy, because of this synergy of printing and etching at the same time. Imagine that you can do etching, but you can also do laser annealing. Imagine you print something. So for example, a silver nanoparticle ink, which we currently use a lot. Silver nanoparticle inks need thermal annealing. Without thermal annealing, they do not have the proper electrical properties. And for that matter, we need to do a thermal annealing in an oven by photonic means, but also by laser. Imagine that we can scan locally on a substrate which is sensitive to even on a substrate which is sensitive to temperature. Since we do it locally, we can have a high gradient of temperature so that we can heat up locally.
I understand. Okay. Any other comments or questions, please? Okay. If not, I will wish to thank Catalin again and all of you for your. There is one question. Sorry, for Boyago, I think it's a guy Boyago. Okay. Seems that he doesn't answer. Okay. So thank you, Catalin, one more time, and all of you for your attendance. See you next time to the next webinar, RIANA webinar in January. I hope it will be the next one. So see you and happy holidays.
Happy holidays. Thank you again. Bye.